Hi all. Let's go ahead and talk about section 6.4, which is still finding volumes of solids of revolution. Now, this is going to teach us another method in this section, though. So the last section we did slicing. And with the slicing method, we either have the simple surfaces where we can do the disk method, where there's just one radius because the entire region is connected to the axis of revolution, or where we had to do the washer method because the region that we were rotating about the axis of revolution was disconnected from the region. So we had an inside radius that we had to hollow out from the outside radius. Okay, the same idea here as far as finding volumes of the solid of revolution, except this time we're going to use a different method called the method of cylindrical shells. First of all, I just want to discuss why do we even need another method? Because you might be thinking, well, I'm good with slicing, so I don't need another method. Well, slicing doesn't always work. I've got an example here that slicing would fail miserably on. It's a rather simplistic problem, too. Let's say I ask you to rotate the region bounded by 2x squared minus x cubed and the x-axis about the y-axis. And of course, I'm asking you to find the resulting solid. Okay, so 2x minus x cubed has x-intercepts at 0 and again at 2. It's going to look something like this, the region bounded between the curve and the x-axis. Now, what I'm trying to do is I'm trying to rotate this region about the y-axis. So I know if I were thinking the slicing method, each of my slices are going to have to be horizontally cut where they have a thickness with respect to y. And they're going to have an interior radius that I would have to hollow out from my formula that had the exterior radius formula of R2, which is going to go from the axis of revolution to the end of this curve here. But now here's the problem. I don't have a formula for what this part of the curve is and this part of the curve is. Why? Well, the reason is because you're not able to solve this equation x solely in terms of y. That's what I'm saying here. You can't tell me what x is equal to only in terms of y. So could you solve for x in terms of x and y? Of course. That's not helpful. So since you can't get x in terms of y and y alone, we're not going to be able to use the slicing method. And the slicing method would be the washer method in this specific instance. Because in order to use the slicing method about a vertical axis of revolution, you would have to get your relation in terms of y. We can't do that. So slicing, not even an option. I say, well, we're going to use cylindrical shells instead. Cylindrical shells, it's really going to tie in a very common thing. Back when we estimated area under a curve using left and right hand rectangles, well, this is that exact same idea, except now if we put a rectangle under the area portion part of a curve, if I want to try to find the volume of the rotated solid, I need to think about what happens as that infinitesimally thin rectangle gets rotated around the axis of revolution. Now, I've tried to show that here with my limited drawing abilities, and what I'm trying to get you to see is that it looks like a can or a cylinder. So I can say, well, I can find the volume formula for that. So what you're supposed to be thinking here is if it's going to if it's going to form some can that has a thickness around the shell casing of delta x, then think about if I ripped that can open. If I ripped that can open, if you go in and you take a Coke can or something like that, if you cut it down the side and rip it open, you're going to get a rectangular solid. And so I can say, well, okay, and now we're not talking about the top and base, we're just talking about what volume would be formed by the sides. And so you could say, well, the volume formed by that rotation as we're going around, if I rip that can open and it forms a rectangular solid, and it will every single solitary time, I know the volume of a rectangle is just length times width times height. And so I start thinking about it. And I can say, well, the length, what formed the base of this rectangle here? And I can say, well, the base of that rectangle is formed by the rotation of this rectangle about this axis of revolution, I can say, well, the rotation is a circle. I know that the length that that rectangle is going to travel around the circle is the circumference of a circle. Well, circumference of a circle is 2 pi times the radial length. And I know that any rectangle that I draw within this region, by definition, it's always a distance of x from the axis of revolution. Any value on the coordinate plane, the definition of how far away it is from the y-axis is defined by x. So this is the radius x, as x is going to go from 0 to 2 in this case. So I can say, well, then the base of this, which is going to form the length of my rectangular solid, is just going to be 2 pi r, which becomes 2 pi x. Now the height, you say, well, the height of that rectangle is going to form the height of my rectangular solid, and it's just going to be the height of my function at any specific value, which is given by 2x minus x cubed. So I have 2 pi x for the base, the height, 2x squared minus x cubed. Well, the thickness, it's just determined by whatever arbitrary thickness of the rectangle you gave in the first place. We call that, by definition, delta x. It's whatever increment in the x-axis you had to go to get from this side of the rectangle to this side of the rectangle. Now we know in order for this rectangle to correctly give me the area under the curve, I've got to put infinitely many rectangles. In the same manner, if I want that rectangle's rotation to give me the correct volume when I rotate this solid around, I need infinitely many of them. So I take the volume for one shell, the circumference of the base times the height times the thickness of the shell. I say that's the volume of one arbitrary shell. Well, I want the volume of the entire rotated solid. So I can just say, well, I need to sum these shells up from where they would begin to where they end. So notice I factored out the 2 pi, and then I said it's the integral from 0 to 2, since x is going to start at 0 and x will end at 2, of x times 2x squared minus x cubed, and of course the delta x becomes dx as it becomes infinitesimally small. So now I can say, well, now it's simple algebra. I multiplied by x on the inside, got my polynomial. I used the power rule to integrate, and then we just evaluate that integral from 0 to 2. As most cases, you don't need to worry about the 0, but you plug in the 2, you'll get 16 over 2 minus 32 over 5. That's simplified to just give me 8 over 5. I multiply that by my 2 pi. I get that this region is going to be 16 pi over 5, and that's going to be in cubic units after we rotate it around. That's how much that rotated solid would contain within it. Now, in a problem like this, please keep in mind, there was no option. Some people say, well, I just prefer the slicing method. I'm going to do it that way. You didn't have a choice. Slicing would not work on this example. So cylindrical shells, you're going to find will always work. It's most of the time people prefer slicing. And to be honest, what I would recommend as you're working these problems, and I'll probably do them on the Achieve assignment this way, anytime the rotation is about a vertical axis of revolution, cylindrical shells is the better choice. Why? Because you get to keep everything in terms of x. Anytime the rotation is about a horizontal axis of rotation, or anytime the rotation is about horizontal axis, shells is not as good because your shell is going to have a width of delta y that time, and you're going to have to get everything in terms of y. In that case, I would rather just use slicing because your slices will have a thickness with respect to x. So I always prefer to keep whatever type of problem allows me to keep x most of the time. There are some exceptions to that, like in cases where one option is not possible. Let's look at another problem with this. So in this one, again, notice I'm giving you a vertical axis of revolution, so shells should be the easier option. I'm asking you to rotate the region enclosed by y equals x and y equals x squared about the y-axis. So x and x squared we know intersects at 0 and at 1. It'd be 0, 0 and 1, 1. My drawing is not the greatest here, but what I tried to show is that the height of my rectangle in there would be the linear function minus the quadratic function, x minus x squared. I'd take that rectangle of that height, rotate it around, and I'm trying to find the volume of the solid of this rotated shell. Well, I know the volume of one shell. If I ripped that shell open, it's just going to form a rectangular solid that has a thickness of the change of x. Its height would be given by x minus x squared, and its base, that's formed by the rotation here. You just say, well, it's the area of the circle, which is always 2 pi r. Once again, r here is just the distance from the y-axis, so 2 pi x. So I get the volume of the shell, base times height times the width, 2 pi x, x minus x squared times delta x. I went ahead and distributed the x through that group when I brought it down here, and I said, well, then that's going to become x squared minus x cubed in there. I'll keep the 2 pi on the outside. The volume of this entire rotated solid from x equals 0 till x equals 1 is going to be the integral 2 pi times the integral of x squared minus x cubed. Power rule tells us that's going to be 2 pi times x cubed over 3 minus x to the 4th over 4 evaluated from 0 to 1. When I evaluate this at 1, of course, we're just going to get 1/3 minus 1/4. Evaluated at 0, you get a 0. 1/3 minus 1/4 would be 1 over 12. 1 over 12 times 2 pi gives me that pi over 6 for my final answer. So I know that this would be pi over 6 cubic units of volume if I took this region and I rotated it about the y-axis. Okay, what if I wanted to rotate about a horizontal axis? Now this is a problem I did in the notes in the last section with the slicing method. This problem is better done with slicing. Just want to show you it could be done with shells. So if I took the area underneath the square root of x between 0 and 2, and I ask you to rotate that about the x-axis. Again, if it's a horizontal axis of revolution, I would recommend the slicing method. But I'll use shells. The problem with a shell in this case is that the region that you're rotating about is anytime it's a horizontal, then you can say, well, then the rectangle within the curve is going to have a left-hand side and a right-hand side, and the thickness of that rectangle is going to be a change in the y-axis. That's extraordinarily important here, is that you understand with shells, you're going to have to integrate with respect to y if you rotate about a horizontal axis. It's the exact opposite scenario of slicing in that regards. So I can say, well, when that rectangle rotates around, it still forms a shell. I think of it as a can on its side. But no matter what, you can still pull apart that can and you're going to form a rectangular solid. This time, that rectangular solid's dimensions, I'll say its base is given by the height of this rectangle. How am I going to get to that? Well, I know that the right-hand side is always given by x equals 2. The left-hand side is, well, our function was y is equal to the square root of x. Excuse me. We know that that's the same thing as x is equal to y squared. So I can say this function is just x equals y squared here. So notice, I said I'm going to call the height of this 2 minus y squared. And again, you cannot call it 2 minus the square root of x. It has to be in terms of y. Has to be. So I just called this x is equal to, I'll go ahead and write it below. Maybe my pen will allow it. X is equal to y squared. And then I go in and I can say, well, all right, now, then right minus left is going to be 2 minus y squared. That's where that came from. Now, where did the height come from? Well, the height came from what would happen if I pulled apart that shell. Well, the height of it would be given by the circumference of the base of that shell. And you can say, well, the circumference, it's always 2 pi r. R in this case is the distance from the axis of revolution, the x-axis, to wherever our curve is at that instant in time. You can say, well, we know our curve, it can be as close as 0 and as far away as the root of 2 up here. That's the largest the radius is going to get. But whatever that is, that's just the y value in any coordinate. So I can say, oh, yeah, by definition, the distance you are from the x-axis is always whatever the y value is. So I can say, okay, then my radial length is y, my circumference is 2 pi y. So then I have the base that I've already discussed, 2 minus y squared times 2 pi y times the thickness of the rectangle, which are all delta y's. Now, I can say the volume of one arbitrary shell that I would pull out from this rotation of the rectangle is going to be the circumference 2 pi y times the height 2 minus y squared times the thickness delta y. I just simplified that by distributing y through that group. Now, if that's the volume for one shell, then the volume of the entire rotated solid. Please make sure you see where I get my limits of integration. So often students will just say, oh, it's integrated from 0 to 2 because we get used to integrating with respect to x. Well, these shells are going to begin when y is 0, and they're going to end when y is the root of 2. Notice from their very original problem, you're told x goes up to 2. Well, when x is 2, y is the square root of 2. So y is going to go from 0 to the root of 2 of your relation in terms of y, 2y minus y cubed. Now, of course, we're integrating that with respect to y. Delta y is, as you put infinitely many rectangles in there, gets infinitesimally small and becomes dy. Now that dy tells us to integrate with respect to y. Well, we do with the power rule. So my inside becomes y squared minus y to the 4th over 4. We evaluate that from 0 to the root of 2. When I plug it into the first term, of course, I get a 2. And to the second term, I would get the root of 2 to the 4th. Well, that's going to be the root of 2. Well, that's going to be 2 squared, which is 4. 4 over 4, 1. I'm getting a 2 minus 1 on the inside. It's easy to factor. We'll just get 2 pi times 1 for a total of 2 pi cubic units from that rotation. Okay, couple of others. Now, and again, in this problem, you might want to just work this out with slicing just to make sure you're capable of getting the same answer. I promise you, if you use slicing on this, that same problem, you get to that same answer and you get there even more quickly. Not that that was difficult with shells, but slicing would have been really a piece of cake. For number 4 here, let's say I'm looking at the region bound between x minus x squared and y equals 0. That's, remember, y equals 0 is just the x-axis. And I'm asking you to rotate that region about the curve or about the line x is equal to 2. So ideally, you always want to use shells about any vertical axis of revolution. Well, we have that here. So I can say I have my vertical axis of revolution at x equals 2, and I'm trying to revolve the region between x minus x squared. Well, x minus x squared is going to have x-intercepts at 0 and at 1. If I plug a 0 into that, y is 0. If I plug a 1 into that, of course, y is 0. So it's just this negative parabola that has a maximum at about x equals positive 1/2, and it's going to go in like this. Now, I'm taking this region and I'm rotating it about x equals 2. Well, instead of trying to draw the whole region, I'm going to draw one shell. So I can say, oh, okay, I could draw a rectangle within this region. Every single rectangle would get rotated about that axis of revolution. And I've tried to draw that here with my limiting drawing ability. But now think about what would happen if we pulled that shell apart to try to find its volume. Well, what's going to be the volume of that shell when we pull it apart? It's going to have a given thickness of whatever change of x we chose to create our original rectangle before we rotate it. That's what this right here is. The base of this shell, well, that's going to be formed by the circumference of the revolution. Circumference of any revolution is always 2 pi r. And what I need you to see here, r is the distance of any rectangle in my region from the axis of revolution. So I can just say, well, every single rectangle is at a distance of x, as x is going to go from 0 to 1. Well, the radius then is going to be 2 minus whatever x is, right minus left. This is at a position of x, this is at a position of 2. Well, then the distance is always 2 minus x. And you can see when x is 1, your radial length will just be 1. When x is back at 0, 2 minus x will give me the whole radial length of 2. So I know 2 minus x covers every single radius throughout the problem. And of course, the height here is just your function's formula, x minus x squared. So now the volume of the shell, I can say, is my 2 pi times 2 minus x minus x squared times the thickness, delta x. You FOIL out that group and get to this. So now I can say, again, that's nice because it's just a polynomial. So I know I can go ahead and write the volume formula for the entire rotated solid by saying it's just going to be 2 pi on the integral, where this formula for the rotation area begins. Well, it's going to begin at x equals 0. It will end at 1. Integrate from 0 to 1 of the polynomial 2x, and I went ahead and gathered my x squared terms, minus 3x squared plus x cubed. We're integrating that with respect to x. We use the power rule. We get x squared minus x cubed plus x to the 4th over 4. We're evaluating that from 0 to 1. And of course, when you plug in the 1, you'll get your 1 minus 1 plus 1/4. So you're just getting a 1/4. 2 pi times 1/4, you get your pi over 2. I am 100% confident if I take that region, x minus x squared, rotated about the line x equals 2, I will get a solid that will have a cubic volume of pi over 2 cubic units. Okay, up next. Now, again, remember I was saying I would strongly suggest using slicing anytime you have a vertical axis of revolution, and I would choose to avoid it if it was about a horizontal axis of revolution, if at all possible. I'll go ahead and show this. I'm asking you to take the curve y equals the negative square root of x up till x equals 9, so that's a vertical line. So it's the region bound between the negative square root of x and x equals 9, the region bound between that and the x-axis here. I'm trying to take that region and rotate it about the horizontal line, y equals 9. Now, it's really hard to see in this drawing what I'm doing, so let me try to make sure I'm explaining it. The region that I'm rotating is between the x-axis here and my curve, which is the negative square root of x. So it's this region right here. Please notice I've drawn a rectangle within that region right here, and I'm trying to rotate that rectangle about the axis of revolution that is up here at y equals 9. So 9 units above the x-axis is y equals 9. I'm rotating each rectangle about that axis of revolution. And I get this rather odd looking, with my lack of drawing ability, shape up here. So I can say, well, okay, no matter how bad it looks, can I get the volume for one shell? Of course I can, because I know that the thickness of every single rectangle I would have to draw in there has to be some arbitrary thickness with respect to y. I go ahead and label the thickness delta y. Well, what's the base of this going to be? Well, that's from this side to this side. How am I going to get that base? I know I'm going to the vertical line x equals 9. That's the right-hand side of this. What's the left-hand side of any rectangle you would draw in there? Well, the left-hand side is going to be your square root formula. Can you say 9 minus the negative square root of x? No, you may not. Why may you not say that? Well, because you can't have it in terms of x. So just like the previous problem, you'd say, oh, I'm going to have to square both sides. Y squared is going to equal x. Negative square root of x, quantity squared, is positive x. I get x is equal to y squared. So I can say, oh, then this is the same thing as x equals y squared. So I would say if x equals 9 minus x equals y squared, 9 minus y squared. That's where that came from. Right minus left. And I had to get it in terms of y. Again, this is x equals y squared there. So now I have the thickness, I have the base. Well, the height. The height is just determined by your circumference. And you say, well, the circumference is always 2 pi r, where r is the distance from the axis of revolution and any rectangle that you're revolving around it. So you say, well, we know that the distance between the x-axis and any of these rectangles is defined as y. We know that the axis of revolution is 9 units up. So I can just say, well, then just say top minus bottom. It's always going to be 9 minus whatever y is, as y is going to range from -3 to 0 in this region. Notice when you're at the value when y is -3, 9 minus a negative y, that's going to give you your radial length of 12. And you can see, yeah, the radial length would be as much as 12. It's going to be as little as 3 when x is 0 and when y is 0. So you can say, okay, then I'll have 2 pi r becomes 2 pi times 9 minus y. So now the volume of my arbitrary shell, sorry, it's a little messy there, you'll have your 2 pi r, 2 pi 9 minus y times the base of the shell, 9 minus y squared, times the thickness, delta y. Carry out the algebra there, I get this polynomial in terms of y. And then I'll just take that polynomial in terms of y, integrate it from where the rectangles would begin in terms of y. They would begin at y equals -3. They would end at the ordered pair 0, 0 when y is 0. So you're going to integrate from -3 to 0. I'll factor the 2 pi out, keep my polynomial in terms of y in there. So now I can use the power rule to integrate. I'll get 81y minus 3y cubed minus 9 over 2y squared plus 1/4 y to the 4th, evaluated from -3 to 0. Usually we have 0 as the lower limit of integration. It's the upper this time. But what hasn't changed is that when you try to evaluate this relation at 0, you're just going to get a 0. So notice I put upper limit of integration is just 0 minus what we get for the lower limit. I plugged a -3 in and I got -243 plus 81 here. And then you have minus 81 over 2 plus 81 over 4. Carry out the arithmetic there, and the inside portion gives you 729 over 4. Multiply that by 2 pi, you're going to get 729 pi over 2. Now, again, this is one of those problems where if you wanted to try that by the slicing method, I think your slicing method would be quite a bit easier there. It'd be the washer method for you to have an interior and an exterior radius, but at least you could keep it in terms of x, and you would just integrate that from x equals 0 to x equals 9. I think it'd be a little bit quicker. But hopefully you're also thinking, hey, this cylindrical shells is not bad either. Now go ahead and please do try the problems in this section. I think that you'll see that these 5 examples cover all the different types that you'll see, but of course I'll also work the problems within Achieve too. So that should help you out if you run into any problems. Make sure you see how I worked any of the problems. I'll be glad to help you if those aren't good enough as you're trying to weave your way through these. Let me know if you need any help.